Okay, in this next problem, it's going to be 20-22. Here's the circuit. And so we're solving everything at resonance. And since that's the case, the first thing we're going to say is what do we got? We have the reactance of the capacitor is going to be equivalent to the reactance of the inductor. All right. And again, this is the circuit without any simplifications, but we use the simplifications or the assumptions in our equation. So we're going to be drawing from the stuff that I summarized on the previous video. And again, I think I mentioned the summary equations that I derived or reviewed. We didn't derive all of them. We actually just stated them and used them. Are called out in the book. I don't have my book here, so I don't know the table number, but if you go into the chapter under 20, especially at the end of the parallel resonance circuit, it has a table summary, and you'll look at the columns. There's one for when Q is greater than 10. That's the column that we're really going to focus on. Then there's another column for Q is greater than 10 and R's equal to infinity. So those are really the two columns that you'll use. And I'll go through this problem, reinforce some of the equations, and then hopefully have enough information, at least get started on the homework, understanding that the homework isn't due until Thursday, the day I get back. I'm not going to want to spend a ton of time on this, my first day back on Tuesday, but I suppose I could probably maybe do one problem at that point. So anyways, again, if you go through these videos, and they're not the easiest things to watch, and they're not the easiest things to understand, I'm sure, pause them, do what you can, and then, in addition, send me any questions, because there's no sense in holding on to a question until that Tuesday I come back and hoping to get it clarified in the one class period. So, anyways, to begin here, Part A for this thing, we're looking to calculate the Q of the inductor. Okay, so since we said that these two were equal, then we can also say this then. I didn't put that in here. Let's put this. This is actually 400 ohms. Okay, so that wasn't in there. That's part of that problem though. So the reactance of the inductor is also going to be 400 ohms, since the capacitor was at 400 ohms. Although I didn't write it in there, it is, and it should be stated that in your book. All right. So knowing that. Our Q for the inductor is going to be the reactance for the inductor, all divided by the resistance of the inductor. And again, these are the values. When we use these values, we're looking at the values in this series branch. Okay, so let's get going here. We have 400. Divide by 8, which gives us, that's an equal sign, gives us 50. And of course, that's greater than 10. So therefore, we can use our assumptions. All right, let's see here. B. Actually, I think B was to solve for Q, and A was to solve for the reactance of the inductor. But I'd already written that out, so we'll just leave that as that, and I think these two are actually switched. All right. C, we were looking for the bandwidth. Okay. So we don't know the series resonant frequency Fs. We don't know the inductor, we don't know the inductance nor the capacitance. So really, we're looking to use the bandwidth being equal to this, right? And we're going to calculate our QP. Let me slide this up here, shrink this and slide it up. We're going to go ahead and calculate our QP based on what we have for the resistance, the series resistance here, and we know it's not infinity, So we know that we have the series resistance in parallel with the Q of the inductor squared multiplied by the resistance of the inductor. And this was all divided by the reactance of the inductor. Now, so again, if you go look back, this is I'm not redrawing the simplified parallel resonant circuits each time. But if you go back, these equations that we use are derived from when we had a simple parallel circuit. Looking at the circuit that we have here, hopefully you realize this is not a simple parallel circuit, right? You have the fact that we have the resistor of the inductor and the reactance of the inductor in parallel. You know, it creates, you know, the so-called series parallel circuit. Okay, so what we've done is we went back, we created a simplified version of this, and it was simplified. In fact, it was strictly an entire parallel circuit. And having done that, we generated all these simplified equations, and this equation that I just wrote down is one of them. Okay. All right, so let's continue on. So we know everything that that we need to know to solve for the quality factor. So let's go and put them in. We got 20K, and that's in parallel with 20K squared times 8 divided by 400, okay? And then if we go ahead and multiply that whole thing out, you're going to get 25, okay? All right, the one thing I failed to mention, and I didn't write this out, is that part C here says finding the bandwidth at, finding the resonant frequency when the bandwidth is at 1K. All right, so that's 1 kilohertz. All right, so going back to the equation there, to solve for the frequency of this parallel resonance circuit, we're going to rearrange this so that we have the bandwidth multiplied by the quality factor of the parallel circuit. All right, so you have the 1K, and again, this is problem 22 in the end of the book, so you should be able to, you know, sort of fill in the spots that I didn't clearly put down that this was at 1K because it wasn't written down here in my notes, but I noticed that I used it and it wasn't provided in the original, so that is in the book at 1K. So anyways, so what do we got? Then we have